This is Paul again with a short script that has some examples related to subsections 1.1 and 1.2 of the executive summary. It doesn't really fit into the mainstream, but I think it may be helpful when you're trying to do some homework problems. So here goes. We'll use the vector library again, changing the name so that it's correctly 1.2L. And the first thing I'm going to do is make a triangle that fits into a square of side 5 but isn't too squished. I've written a little function to do this. You don't have to worry about the details. It just keeps trying till it gets a triangle with a big enough area. And once I've got a reasonable triangle, I can extract from a list of 3 vertices the points A, B, and C that define the triangle. Here I've made a list of vectors because in R you can't make a vector of vectors. This is a subtlety you shouldn't worry about unless you're a hardcore computer scientist. I've now got 3 points A, B, and C, and you can do this whenever you want a randomly generated triangle. And there are the points A, B, and C plotted on the screen. Once I've got the 3 points, I can subtract them to make vectors and draw arrows to represent the vectors. Now, using the norm with a capital L function, I can display the length of each side and write it across the middle of the side. I can also, using the angle between function based on the dot product, calculate the angle at each vertex in degrees and write it next to that angle. And this is the convention you're probably used to from the course in which you took trigonometry. The side opposite the vertex C is labeled little c. Now we're all set to check some famous formulas of trigonometry. The way I defined angle by saying that the cosine of the angle between 2 vectors is equal to the dot product of the vectors over the product of their lengths makes it not at all obvious that the 3 angles in a triangle have to sum to 180 degrees. So let's start by checking that. What do you know? 180 degrees on the dot. Do you remember the law of sines? The law of sines says if you take the ratio of the sine of the angle at each vertex, it's expressed in degrees, so I have to use sine with a capital N, a capital S, to the length of the opposite side. You get the same ratio in each case. Yes, indeed, we got the same ratio 3 times. I can check the law of cosines, which is a generalization of the Pythagorean theorem. It says for a triangle that's not necessarily a right triangle, the square root of the square of the first side plus the square of the second side minus twice the product of the lengths of those sides times the cosine of the angle between them, which would be 0 if that angle were a right angle, is equal to the length of the third side. That works too. And then there's a whole lot of ways of calculating the area of that triangle. I can take 1/2 the area of the parallelogram that I get by using 2 of the vectors, or I can use one side of the triangle as the base and calculate the height, getting the same answer. Or if I'm really into ancient Greek mathematics, I can use Heron's formula, which expresses the area of a triangle solely in terms of the side length. You need to start with half the perimeter and then take that times half the perimeter minus the first side, times half the perimeter times the second side, times half the perimeter of the third side. That product has the dimensions of the 4th power of the length take the square root, it has the dimensions of area, and it is indeed the area. Or finally, I can calculate the area of the triangle by computing the magnitude of the cross product, which you may recall can be obtained by taking the product of the lengths and subtracting off the square of the dot product. So you might find this useful in doing some of your homework problems.